Hi there, you are watching a video of shell and tube heat exchangers for industrial plants. Next, the main parts of the shell will be described. Shell and tube heat exchangers are formed by three external elements: the stationary head, the shell, and the rear head. The function of the stationary head is to receive the fluid that has to circulate inside the tubes, distribute it and collect it to send it out of it, that is, back to the process. One of the main parts of a shell and tube heat exchanger is the shell. The shell is a one-piece cylindrical body. It can be a tube or a rolled metal sheet, welded if needed. It will contain the tube bundle inside, and also it is worth mentioning that the fluid that bathes the outside of the tube bundle circulates through the interior of the shell. Finally, the rear head has the function of returning the fluid to the stationary head in heat exchangers with more than one pass in the tube side. The internal pressure is the most common loading in this type of equipment. For most applications, pressure vessels are either spherical or cylindrical. Depending on the application, pressure vessels will adopt one shape or the other. In a spherical vessel, the internal pressure is acting equally in every point. This means that the wall stresses will be the same in every direction. This is not happening in a cylindrical vessel, where due to the asymmetry of this shape, the wall stresses vary with direction. That is why a sphere is the optimal geometry for a closed pressure vessel in the sense of being the most structurally efficient shape. This could be explained looking closely at one infinitesimal element. In the cylindrical vessel, the internal pressure is resisted by the hub stress or circumferential in arc action, whereas the axial stress does not contribute. In the spherical vessel, the double curvature means that all stress directions around the pressure point contribute to resisting the pressure. That is why, for the same diameter and design conditions, the maximum normal stress in a spherical pressure vessel is 1/2 as large as that in a cylindrical one. Therefore, the wall thickness follows the same relationship. As previously mentioned, this means that a spherical vessel is the most structurally efficient. However, the cylindrical shape may be more convenient to fabricate and transport, among other things. With the aforementioned in mind, now we will review the equations proposed by the ASME code, section 8, division 1 for the shell. Due to the geometry of cylindrical shells, the required thickness for the shell will be the higher value of the hub and longitudinal stresses verification. The required thickness is a function of the inner radius, the design pressure, the joint efficiency, and the maximum allowable stress of the material at design temperature. There are several types of heads or covers to close cylindrical vessels. Among others, the following are included: flat, spherical, elliptical, hemispherical, conical, etc. Let's review the equations proposed by the code for these elements. Elliptical heads are the most used type. One of the main features is that the height of this head is exactly half the radius, which is why they are known as elliptical 2-to-1. The thickness required for elliptical heads is practically the same as for cylindrical shells. The variables intervening in the required thickness calculation are the same as in cylindrical shells. This type of head is used to contain large volumes and to withstand high pressures. The thickness required for a hemispherical head is practically half as for cylindrical shells. The variables intervening in the required thickness calculation are the same as in cylindrical shells. These heads are very similar to elliptical ones, where the height of the head is variable and normally lower than in the case of elliptical. Once again, the variables intervening in the required thickness calculation are the same as in cylindrical shells. Generally, flat covers are tailored for each shell and tube heat exchanger. Blind flanges can be used in some cases, as long as the dimensions coincide with those of the exchanger. Rare occasions, actually. Both the ASME Section 8 Division 1 code and the TEMA code include procedures for calculating the thickness of a flat cover. Both procedures determine the flat cover thickness using the same principles and arriving to similar results. Depending on the client and project requirements, one of these two design codes is applied. Let's review the proposed equations by the TEMA code for flat covers. Flat covers must be designed for the most critical condition. Due to the complex load system acting within the heat exchanger, shear and bending stresses are present in the calculation. The required thickness according to the TEMA code for flat covers is a function of the design pressure, the gasket mean diameter, nominal bolt diameter, the radial distance between the gasket mean diameter and the bolt circle diameter, the total cross-section of bolts, and the flat cover module of elasticity at design temperature. Now let's review the proposed equations by the ASME code for flat covers. In this case, the required thickness according to the ASME code for flat covers is a function of a factor depending on the type of joint between the flat cover and the cylinder, the flat cover material allowable stress at design temperature, the bolting load, the flat cover thickness, the design pressure, the gasket mean diameter, and the radial distance between the gasket mean diameter and the bolt circle diameter. As mentioned before, flat covers are generally tailored for each shell and tube heat exchanger instead of standard flanges. This element can be fabricated out of plates or out of forgings. While plate fabricated are less expensive and normally delivering thicker designs, forged ones generally have higher level stresses, requiring longer lead times though. When it comes to designing a conical transition, there are many possible arrangements. Depending on the surface of the pressure vessel, conical transitions can be concentric or eccentric. The calculation method is identical for both configurations, with some special considerations for eccentric reducers. Conical shells and transition sections might be designed with knuckles, without knuckles, with reinforcements, etc. For transition sections between two cylindrical shells of different diameters, it can be selected one of the following: a simple conical section without knuckles, or a conical reducer with a knuckle at the large cylinder, or at the small cylinder, or both. Conical transition sections with knuckles present better alignment with cylindrical shells, and stresses due to discontinuities are lower. However, they are more expensive to fabricate. The cone itself is just one element of the conical transition. In order to design this part, the following aspects should be taken into account. The shell thicknesses due to internal and external pressure for both large and small diameters. The thickness of the knuckles. These elements are included to avoid overstresses in the area. The cone thickness itself due to internal and external pressure, and reinforcement requirements for the cone to shell joint. In the following slides, we will see the proposed equations by the code, section 8, division 1, for conical transitions. For conical transitions without knuckles and with half apex angle less than 30 degrees, applicable equations are the same as for conical heads. The required thickness is a function of the inner diameter, the design pressure, the joint efficiency, and the maximum allowable stress of the material at design temperature. If angles bigger than 60 degrees are necessary, knuckles must be used in order to avoid large stress concentrations in the junction. This means using toriconical transitions. Once the required cone thickness due to internal pressure has been calculated, the cone to shell junction must be evaluated. If the conical transition doesn't have knuckles, there is a stress discontinuity in the cone to shell junction, mainly due to the effects of internal pressure and axial loads, caused by the self-weight, for example. These loads could overstress the area. Therefore, it is necessary to verify if reinforcements are required. The verification procedure is indicated in Appendix 1.5 of the code. In order to reinforce the area, the moment of inertia must be increased by increasing the thickness of the components or by means of stiffening rings. As mentioned before, in order to avoid stress concentration effects in cone to shell junctions in pressure vessels operating at high pressure or with heavy axial loads, conical transitions with knuckles are used. These transitions are called toriconical. Knuckle radius will not be smaller than 6% of the diameter of the cylinder, or 3 times the thickness of the cone. The thickness calculation methods for this transition follows the same considerations as for transitions without knuckles, using DI instead of D. The knuckle at the large end is also known as flange, whereas the knuckle at the small end is known as flare. The required thickness for the large end knuckle, or flange, is obtained according to paragraph 14D, included in Appendix 1. A thickness calculation method for small end knuckles, or flares, it is not outlined in the ASME code, section 8, division 1. An accepted design method to obtain this thickness is the pressure area method by Sick and Germain.